Hello and welcome to section 2.2 on the limit of a function. In section 2.1, we saw how a tangent line can be found by noting the trend of secant lines. This trend is called a limit. Let's take a closer look at this concept. Let's take the function sin x over x. Recall from your pre-calculus class that the domain of f is all real numbers, except for 0, as division by 0 is not defined. This means that f of 0 does not exist. There is a hole in the graph exactly at x equals 0. There may be no point at x equals 0, but we can ask the question, what y value is the function f approaching as the x values get closer to 0? This question is describing the concept of a limit. That is, the limit of a function f as x approaches a value a is the y value f approaches as the x value gets closer to a. Mathematically, we use lim to denote a limit. Below lim is the value x is approaching, and to the right is the function we are interested in. Looking at the graph, it may seem as if the function f really wants to be defined at x equals 0. This feeling is caused by the position of the points surrounding 0. There is a trend towards the y value 1. If we zoom in, at this magnification, it becomes clear that the points surrounding x equals 0 are close to y equals 1. As we increase the magnification, this becomes clearer and clearer. However, there continues to be a hole in the function at x equals 0, as f of 0 is not defined. That is, f of 0 does not exist, but as x gets closer to 0, f values get closer to 1. Let's investigate the rational function f. The domain of this function is all real numbers except 1, as division by 0 is undefined. F of 1 doesn't exist, but what is the limit as x approaches 1? In our graph, the values about x equals 1 are trending towards y equals 1. Let's zoom in. We still see the same trend in this magnification, and in this magnification, almost all values are near y equals 1. As the limit is 1, no matter how high the magnification, we will still observe the points near x equals 1 as having y values very near 1. When describing the graph of a function, we have two topics that can describe locations on the graph above x equals a. The actual value, f of a, and the trend, the limit, as x approaches a. The limit of f as x approaches a, being L, means that you can make the values of f arbitrarily close to L by choosing x values sufficiently close to a. A way to visualize the limit as x approaches a is to imagine ants crawling along the graph of the function towards x equals a. There are only two directions that an ant can crawl from: the positive side, the right side, the points on the curve where the x value is greater than a, and the negative side, the left side, the points on the curve where the x value is less than a. I'll refer to the negative ant as lefty and the positive ant as righto. If the ants meet when they approach x equals a, then we say the limit exists, and if the ants fail to meet, then the limit does not exist. For this graph, lefty and righto meet, so the limit exists. If we break the graph, we obtain a function where lefty and righto do not meet, so the limit does not exist. The y value that righto approaches is called the right-hand limit, while the y value that lefty approaches is called the left-hand limit. A right-hand limit is denoted by a positive behind a, while the left-hand limit is denoted by a negative behind a. So when we imagine that lefty and righto meet at x equals a, we are observing the left and right-hand limits being equal. A limit exists only if the left and right-hand limits are equal. Let's discuss the limits of the function f as x approaches a, b, and c. When lefty and righto crawl towards x equals a, they will meet at the value s. This means the limit as x approaches a is s. However, the actual value of f at a is r. Remember, the limit and the actual value are not necessarily the same. When lefty and righto crawl towards x equals b, they do not meet. They would have to jump to meet. The limit as x approaches b does not exist. Note, the actual value does not have to equal either one-sided limit. In fact, the actual value doesn't have to exist at all. When lefty and righto crawl towards x equals c, they are challenged with a huge climb. If an ant would have to crawl upwards or downwards indefinitely, as is the case here, then we say that the limit is infinite. In this case, the left-hand limit is negative infinity, and the right-hand limit is positive infinity. Be careful. When limits are described using infinity, they actually do not exist. We take note because they fail to exist in an interesting way. The term infinity is not a number to be used in calculations. It is a term to indicate unboundedness. There are three scenarios in which a limit exists and is equal to a value L. In all three, lefty and righto meet at x equals a. In the first scenario, the actual value f of a exists and is L. In the second scenario, the actual value exists, but is not L. And in the third example, the actual value does not exist. It is important to note that the limit and actual value are separate concepts and do not necessarily coincide. However, we are interested in when they are equal. We call this continuity. We'll discuss more about this later in the chapter. A few minutes ago, we had an example with ants crawling infinitely upwards or downwards while approaching x equals a. Whenever a one-sided limit is infinite, we say that the function has a vertical asymptote at that location. In both y equals 1 over x and y equals 1 over x squared, there are vertical asymptotes at x equals 0. To summarize this introduction, given the graph of a function, you should be able to identify left and right-hand limits, identify two-sided limits, and identify infinite limits and vertical asymptotes. You've seen the basics. Now work towards mastery through practice and study.